Hello, welcome to my YouTube channel, and today I'm going to be talking to you about Dalton's law of partial pressure. You probably must have heard of the topic kinetic theory of gas. So this Dalton's law of partial pressure is one of the subtopics under Dalton's kinetic theory of gases, and let's just see what the partial pressure, Dalton's law of partial pressure says, and what it's all about. Now, the guy called John Dalton, this is named John Dalton, some years ago, he did an experiment on the pressure of gases, and then he came to a conclusion that for gases that do not combine, their total pressure is the sum of each individual pressure. Now let me explain this. For gases that do not combine, so let's assume we have two gases that cannot combine. So if I want to know the total pressure of the whole gas, so these two gases that do not combine are in a container. All right, so let's say nitrogen and let's say argon in a container, right? So I want to know the total pressure of the gases in this container, and those two gases cannot combine. So what's going to happen is that I'm going to look for the pressure of argon separately, look for the pressure of nitrogen. So the total pressure of gases in this container would be the pressure of nitrogen plus the pressure of argon. So Dalton said that for gases that do not combine, the total pressure is the sum up of every or each individual pressure. So the total pressure of gases in this container is going to be the total pressure is going to be pressure of nitrogen plus pressure of argon, right? If we have three gases in this container, let us say that we have nitrogen, argon, and fluorine. The total pressure of gases in this container is going to be pressure of nitrogen, pressure of argon, plus pressure of chlorine. If we have more gases in this container, the total pressure will be the pressure, the sum of the pressure of each of them. Now, all that is trying to say that if you want to know the pressure of gases that do not combine, and these gases are together in a container or wherever, all you have to do is know the pressure of each, and once you know the pressure of each, you can combine the whole thing together to get your total pressure. So this led us to the formula or the expression P total equal to just a minute. So this led us to P total. I'm going to clean this. P total is equal to the pressure of gas A represents just any gas at all, plus the pressure of gas B, plus the pressure of gas C, and it can go on and on. So it could just be the pressure of gas A and gas B. It could just be the pressure of gas A, B, and C. It could be the pressure of gas A, B, C, D, A, B, C, D, E, A, B, C, D, E, F, just depending on how many gases that you find in a container that do not combine. So the total pressure is going to be the pressure of each, the sum of each individual pressure. And this was one of the expressions formed by Dalton's law of partial pressure. So let's say in a container contains nitrogen and helium, and nitrogen has a pressure of 10 kilonewton per meter square, and helium has a pressure of 5 kilonewton per meter square. What is the total pressure in that container? The total pressure in that container is going to be the pressure of nitrogen, which is 10, plus the pressure of helium, which is 5. So I'm going to have 15 kilonewton per meter square. Alright, so we've seen this. I'm just going to reiterate. Dalton's law of partial pressure is all just talking about gases, or looking for the pressure of gas, the total pressure of gases that do not combine. So if I'm trying to look for the sum of or the total pressure of gases that do not combine, I have to know the individual gases and then sum them up. Now, hope you got that. So another thing we have under Dalton's law of partial pressure is gases collected over water. We're going to solve some questions here. And almost everywhere, if you're an exam student, the student who is writing WAEC or JAM, there's a high chance that you're going to see a question from this topic, gases collected over water. And a lot of students fail this question, a whole lot of students, as much as it is really, really easy. Okay, so you're going to see questions on that gases collected over water. And I'm going to explain this to you. Now, when a gas is passed through or collected over water, there is a tendency that that gas will become wet. Now, when we are looking for our gases, we are solving questions on that gas laws. Do you remember that what we are actually trying to get is the properties of the gas itself, not a gas mixed with something, not a gas, not a solution. Okay, so if a gas is passed over water, there's a probability that this gas is going to become wet, meaning that the gas itself, which was dry, let's call it dry gas, now has some amount of water attached to it. Okay, so if I want to get the true pressure of that gas, how I'm going to get the true pressure of that gas is that I'm going to say pressure, the total pressure that gas that has been collected over water now has is the pressure of the dry gas plus the pressure of the water vapor. Now, when a gas is passed through water, of course, like I said, it becomes wet. It's no longer by itself. So that gas, the dry gas, now has some level of water vapor attached to it. So the total pressure of that gas at that moment is going to be the dry gas plus water vapor. But if I want to get just the gas itself, the original and dry gas, the pressure of the dry gas, what I have to do is that I have to find out the amount of water vapor that was attached to the dry gas, and I'm going to remove it. So the total pressure or the pressure of the dry gas then becomes our total pressure now, which consists of the pressure of the dry gas and the water that is attached to the gas minus that water. So we're removing the water vapor that was attached to it. So once you remove the water from this, you're going to get your dry gas. Because what we are going to be needing in solving for our gas laws is our dry gas. We are not interested in a solution or in a gas that has water in it. We are very, very much interested in gases that are dry. So you see a question, and that question says a gas was collected over water. Guys, the first thing you would have to do or you'd look for is the water vapor that was attached to that gas and go and remove it. That becomes your pressure, your original pressure. Now let's see a question under this. While we solve this question under this particular topic, we are going to understand this better now. Quickly. So I'm just going to clean this. So here's a question under Dalton's law of partial pressure that explains what I just said to you. And I said to you that you see a question and then you see this collected over water. It means that that gas now has some amount of water attached to it, meaning that the gas becomes wet. But what we need in solving questions like this is our dry gas and not a wet gas. So for us to proceed, we have to remove the pressure of the water attached to the gas. So this question says 20 m cube of hydrogen were collected over water. This means that hydrogen here is now wet. So when you see this question, the first thing that you should run to is know the pressure of the gas that was collected over water. So let's go at 17 degrees Celsius and 79.7 kilonewton per meter square. Now, if you've been following, if you've seen order of the preceding topics before this, you're going to know that kilonewton meter square means pressure. It's the unit for pressure. So when I see ATM, kilonewton meter square, or newton meter square, or I see ATM, I know that that value is talking about pressure. So this is the pressure, but then this pressure includes the pressure of the dry gas and the pressure of the water attached to the dry gas. So what you do first of all in questions like this is to subtract the water attached to this pressure from it. Now come here, vapor pressure of water is 1.90. So what I'm going to do is to subtract this vapor pressure of water from this total pressure. So remember our formula, total pressure is equal to pressure of dry gas plus pressure of water vapor. Okay, so my total pressure here is 79.7. My pressure of dry gas is what I want to look for. My pressure of water vapor is 1.90. So my dry gas, the pressure of dry gas is going to be 79.7 minus 1.90. This is the pressure of our dry gas. So subtracting this, what we're going to have, this from this, we're going to have 79.7 minus 1.90. This is giving us 77.8. So the answer to this, the dry gas is 77.8 kilo Newton per meter square. Now, when you see this kind of question, the moment you see was collected over water, like I said, the first thing you should do, you should run and look for the pressure of the gas that was collected over water. After you do that, subtract the pressure of water vapor from that pressure, because the pressure that was given to you is the total pressure. Now, once you do this, this becomes very easy to solve, because all you have to do is to use the general gas equation to solve it. Now I have my pressure as 77.8, and I'm going to call this my P1. So my P1 becomes 77.8 kilonewton per meter square. So cleaning this, I'm going to have P1 V1 over T1 equal to P2 V2 over T2. My P1, the question says my P1 becomes this, right? Remember the question started with 20 dm cubed, so this becomes my V1. V1 is equal to 20.0 collected over at this degree Celsius means temperature. So my T1 is equal to 17 plus 273, which it's going to give me, so this 290 Kelvin. My P1 is 77.8, so I have that here. I'll calculate. A says the pressure of dry hydrogen at this temperature. Ouch. So we've already answered A, which is this. This is the pressure of our dry hydrogen gas, 77.8. The volume of dry hydrogen gas at STP. So the volume of this is, so we have, the question says at STP. Remember I told you that whenever you are asked to solve anything at STP, you should use the standard temperature and the pressure you know. Now, what determines especially the value of your pressure here would be what you were given, the unit of what you were given. So since this is kilonewton per meter square, already that's been given to you here. But if you were not given this, you have to know, these are things that you just know. It just has to be in your head that once you see Newton per meter, kilonewton per meter square, the value is 101.3. Once it's just Newton per meter square, the value is 1.01 times 10 raised to the power of 5. I explained this in the former videos I've made about gas laws, so you should go and watch them to understand better. Now I have V1, T1, and P1. My P2, remember I said standard pressure. So standard pressure, we've been given standard pressure. So P2 is equal to 101.3 kilonewton per meter square. And V2 is what we're looking for, right? T2 standard temperature is what? 273 Kelvin. So let's impute all of this here. So my P1 is 77.8. So I have 77.8. V1 is 20 over T1. T1 is 290 equal to P2 is 101.3. V2 is my unknown, volume of dry hydrogen gas. So I'm looking for volume. And my T2 is 273. So all I'm going to do at this stage is to cross multiply this times this times this divided by this and this, because these are the things holding the unknown. So my V2 is equal to 77.8 times 20 times 273 divided by 290 times 101.3. So equal to, because I'm going to clean this thing right now. We already have the values here. So equal to, so we have 77.8 times 20 times 273 divided by 290 divided by 101.3. Okay, so this is 14.45 dm cube. Okay, so I have my volume in dm cube, right? So I'm going to call this dm cube. All right, so all 14.50 or 15 dm cube, just depending on the options that you have in that question. I hope you understand this. All right, we're going to look at one more question under calculating gases collected over water, and then we move on to the next thing that we have to do. So we have this: two flasks were connected by a narrow tube with a closed tap. One flask contains 300 cm cube of oxygen at 1.0 times 10 raised to the power 5, while the other contains 200 cm cube of nitrogen at 2.0 times 10 raised to the power 5. After opening the tap, calculate the partial pressure of each gas. B, the total pressure of the mixture at constant temperature.